would it be if you could score the bullseye on your first try every single attempt? Well, that's definitely possible, and in this video I'll show you exactly how you can achieve this cool ability. So first of all, we see that the cannonball traveled both vertically and horizontally, which means that the cannonball had both vertical and horizontal velocities. These two pieces of information are key to understanding and deciphering any projectile motion problem. So, how do we calculate the vertical and horizontal velocities? It's actually not as hard as you might think. Let me show you. Imagine you shot a cannonball at a speed of 10 meters per second and at an angle of 30 degrees from the ground. We would have to calculate the vertical and horizontal velocities. Now you might notice that this looks exactly like a right triangle, and we can actually redraw this diagram in that form. Side length A would be the vertical velocity, and side length B would be for the horizontal velocity. Now to solve for vertical velocity, we first need to take the sine of 30 degrees, which is the ratio of the opposite side to the hypotenuse, and in this case is A divided by 10. Now we have to solve for A, and our vertical velocity is 5 meters per second. A horizontal velocity has a similar process, except this time we have to use the cosine of 30 because we need the adjacent side to the hypotenuse. Then we solve for B like normal, and our horizontal velocity is 5 times the square root of 3 meters per second. But more important than the answers we got are the equations that we used to derive these answers. Specifically, I'm talking about these two equations outlined in red. The reason they're so important is because they show us exactly how to use the information we have in order to get the answer that we need. And that means they can actually be converted into general forms that can be used in any scenario that we want. Let me show you what I mean. From our previous example, we saw that the vertical velocity was 10 times the sine of 30 degrees, and the horizontal velocity was 10 times the cosine of 30 degrees. Now, the way we generalize these equations is by replacing the number values with the variables that they represent. So up here, the 10 we know represented the initial launch velocity, so we can replace 10 with v initial for initial velocity. We can do the same thing down here, replace it with v initial, and then the 30 we know represented the angle at which it was launched. So we can replace 30 with angle. Then we can do the same thing down here. Now we can add the variables and switch them down to the variable section. And take a look at this. Now we can adjust the initial velocity and the angle to any value we want, and the program shows us the exact vertical and horizontal velocities for our conditions. That's really cool. Now the next step we have to do is figure out how the vertical and horizontal velocities affect the trajectory of the cannonball, which involves height and distance. The vertical velocity affects the height, while horizontal velocity affects the distance. So let's take a look at how that happens. So let's observe the trajectory of the cannonball. We can see that the force of gravity causes the vertical velocity to decrease by 9.81 meters per second each second. That's why the cannonball has this curved path instead of having a straight diagonal line path. On the other hand, horizontal velocity actually stays constant the entire way through. The reason that the gravitational force doesn't interfere with horizontal velocity is because gravitational force is only a vertical force, and vertical forces cannot interfere with the horizontal velocity. With this information in mind, we can now ask ourselves two main questions that can help us complete our setup. The number one question is, how long does it take for the cannonball to travel a certain distance, which is horizontal? And number two, how long does it take for the cannonball to travel a certain height, which is vertical? Since we know that the horizontal velocity is always constant, it's obviously a bit easier to calculate the horizontal distance rather than the vertical height. So let's start with the horizontal distance with a simple example. Imagine we had an object that was traveling at 5 meters per second horizontally. How long would it take to travel 15 meters? Well, this is a pretty simple problem. All we have to do is ask ourselves, 5 times what equals 15? And then to solve this, we do 15 divided by 5 and we get 3 seconds. Now this is another one of those equations that we can actually convert into a more general form that can be used in any scenario. So if we come back to this, our equation was 15 divided by 5 equals 3 seconds. So now to generalize this, we have to replace the number values with the variables that they represent. We know that 15 represented the distance that the object was supposed to travel. We know that number 5 represented the velocity, which was horizontal. And then we know that the 3 represented the time in seconds, and that we can represent as the letter X. And I'll just change this to the color green. So now, this function right here tells us exactly how long the cannonball should take to travel a certain distance based on what its horizontal velocity is. That's our answer to the first question, the first main question that we had before. Unfortunately, calculating the height based on vertical velocity isn't as simple, and the reason for that is, as we discussed before, the vertical velocity is constantly changing due to the force of gravity. So what can we do in this situation? Well, we can try to create a function that models the velocity over time, and then we can use that function to calculate the height over time. So let's try it out. We know that every second, due to the force of gravity, the initial vertical velocity decreases by 9.81 meters per second every second. And we can say that time in seconds is modeled by the letter t. And then we can make all this equal to v, which is the vertical velocity at any instantaneous point in time. And I'll just change this to a purple dotted line for velocity. So this function right here shows us the exact velocity at any point in time based on the vertical velocity, which is its starting point. So now we can try to use this function to calculate the height of the object, in this case a cannonball. But still, we can't simply do velocity times time equals height because the velocity is constantly changing. We have to use some sort of average value over the time interval we want. And luckily for us, that's actually very easy. Since the velocity is modeled by a linear equation, finding the average value of the linear equation over any certain time interval would just require us to add the initial and final velocities and then divide them by 2. So let's do that. We can say that v initial vertical velocity, which is v vertical, and then plus this expression, which models the final vertical velocity of that time period, divide that all by 2 or multiply by 1/2 equals the average velocity over a certain time period. Now we can plug that into the simple equation for height, which is velocity times time. So we can say h for height equals average velocity times time. And let me change this to a blue graph. So now this blue curved function right here symbolizes the height of the cannonball at any point in time based on its velocity. And that brings us to the final stretch of our efforts. We already have 2 equations that tell us the vertical and the horizontal velocities of the cannonball. We have down here all of our variables, and most importantly, we have these 2 equations that answer our 2 main questions from before. This equation right here, which we just did, tells us the exact amount of time that it takes for the cannonball to reach a certain height, while this equation down here tells us the exact amount of time that the cannonball takes to travel a certain distance horizontally. And a key point to add to that is that the answers to both of our questions must be equal in order for us to hit the bullseye. So now the final thing we have to do is just plug in values for our variables based on the scenario that we have. So let's see here. Let's try to keep the angle of launch and the target distance constant, and let's only try to change the velocity so that we get the bullseye. Let's plug in the constants first. The angle is 50 degrees and the distance is 15 meters. Now we have to figure out a velocity value where the answer to this equation and this equation is the same. In other words, the green line and the blue line should intersect at the x-axis, which is the height 0, and that's the height of the target. So let's try to first plug in maybe 10 meters per second as our velocity. Now let me take out this velocity line just so it becomes clearer. We see that the green line is a bit ahead of the blue line. That tells us that with the velocity we have right now, 10 meters per second, the projectile, the cannonball, will fall short of the target. It will hit the ground before it actually reaches the horizontal distance of the target. So that means we have to increase the velocity. Let's increase it to 11. Let's try 12, 13. Okay, so 12 looks like the closest whole number that we can get. Now, unfortunately, the simulation doesn't allow us to put our velocity in decimal values, so we have to stick with the closest whole number we can get. But it's possible for us to get even closer by adjusting the target distance slightly. How do we do that? Let's see. From this right here, we see that the blue line is still a little bit behind the green line. That means the projectile will fall to the ground a little bit before it reaches the actual bullseye. So let's adapt to the time it takes for it to fall to the ground, which is 1.8741 seconds. Let's type that right here, 1.8741, and then multiply that by the horizontal velocity, which is 7.71, and we get 14.45, or we can round that up to 14.5. So this is the actual distance that it needs to be in order for initial velocity of 12 to work. So let's move the target to 14.5 meters. Alright, this is it. We're gonna launch it and let's see if we get the bullseye.